If x and y are two random variables, then we define the covariance of x and y as the expected value x minus its expected value multiplied by y minus its expected value. We have a couple of very important covariance results. Let's begin with the first one. If we expand the parentheses inside the expected value, we see that this is equal to x times y minus this times this, x times mu y minus this times this, mu x times y, plus the final one, mu x times mu y. Since I have pluses and minuses here, I can move the expectation operator inside. So it's x times y minus expected value x mu y minus expected value mu x y plus expected value mu x mu y. This term I can't do anything with. I cannot move the expectation operator inside unless I know that they're independent. So we'll just write xy. For the next term, we realize that mu y is a constant, and constants, they do go outside the expected value. Mu y, expected value of x. Same thing, mu x is a constant. For the final one, I have a product of two constants, so that's a constant. And the expected value of a constant is that constant itself. So I get this. Expected value of x, that's just simply another term for mu x. And this is just another term for mu y. So I have expected value xy minus mu y mu x minus mu x mu y plus mu x mu y. I can cancel one of them and I have an important result, namely that the covariance between x and y can just as well be written as the expected value of the product minus the product of the expected values. The second important covariance result is the following. If x and y are independent random variables, then the covariance must come out to be 0. This is not hard to show if we use the first one. Covariance of x and y is expected value of x times y minus mu x mu y. If x and y are independent, then we know that the expected value of the product is the expected value of x times the expected value of y. That's only true if they're independent. And that's mu x mu y. So I get mu x mu y minus mu x mu y. So that must come out to be 0. Independence implies 0 covariance. The opposite is not true. All we have to do is just give one example where it's not true. And I think a very nice example is the following. X can take two values, minus 1 and 1. Y can take three values, minus 1, 0 and 1. And the probability mass function is given in this table. We get the marginal PMF of x by summing the column. So that's 1/2, 1/2. 50-50 chance for x to be minus 1 and plus 1. We get the marginal of y by summing each row. 1/4, 1/2, 1/4. So we easily see that mu x is equal to mu y is 0. Both of them have expected value 0. So what's the covariance between x and y? Well, go through all 6 cases, which will only be 3 because the PMF is 0 in 3 cases. So if we do this case, it's minus 1 times minus 1 times 1/4. For this case, 1 times 0 times 1/2. And for the final case, minus 1 times 1 times 1/4, which comes out to be 0. So we have an example where the covariance is 0. If you look at the probabilities, this kind of makes sense. When x is large, equal to 1, then y will not be either typically large or small. It would be 0 for sure at its expected value. When x is small, the same thing holds. Y will not be bigger or smaller than its average, it's -1 or +1 with equal probabilities. So the covariance is 0, but we clearly see that these are not independent random variables. There is a really strong dependence between them. When x is 1, I even know the value of y. It must be 0. And we can check it formally because remember, for independence, the joint PMF has to be the product of the marginal PMFs. So if I check for, say, well, you can pick any one pretty much, x equal to 1 and y equal to 0, this one right here, then the PMF, f of x comma y, is 1/2, while the product of the marginal PMFs, that would be 1/2 times 1/2. That's not equal to fx of x times fy of y, which is 1/4. These are highly dependent random variables which are still uncorrelated. Basically, the reason this can happen is that for the covariance to be 0, there's just really one condition that has to be fulfilled, and that is that the expected value of the product must be equal to the product of the expected values. For independence, on the other hand, we have 6 conditions that needs to be satisfied. For every possible value of x and y, the joint must be equal to the product of the marginals. So that is way harder to satisfy. And this is also why independence is a much stronger condition. It tells us way more than simply 0 covariance does. There is one really important exception to this rule that independence is a stronger condition than 0 covariance, and that is in the case when x and y both follow a normal distribution. Together, they follow what's called a multivariate normal distribution. In this specific case, 0 covariance and independence turn out to be the same thing. So in this particular case, if they are uncorrelated, then they will also be independent. But this does require the specific distribution of the random variables x and y, and it's not something that we can count on in general. The fourth one simply states that the covariance between a random variable and itself comes out to be exactly the variance of that random variable. Not hard to see. The covariance between x and itself is the expected value, x minus its expected value, and x again minus its expected value. Well, that's just simply the same as x minus mu x squared. And this is precisely how we define the variance of x. The fifth one is very important as well. It says that the covariance between a random variable and a constant is always 0. Random variables do not covary with constants. Kind of makes sense, right? Because a constant doesn't vary at all, so it will not covary with x. Formally, we can prove it as well. So that's x minus mu x times. We can always view a constant a as a random variable. It is the random variable that returns a no matter the outcome of the experiment. So I can do a minus the expected value of a. Well, the expected value of a is just a itself. So this comes out to be 0, and the whole thing comes out to be 0. Number 6, the covariance between the random variable x and y is the same thing as the covariance between y and x. It doesn't matter in which order I put x and y. This simply follows from the fact that the multiplication is commutative. This thing is just the expected value, x minus mu x, y minus mu y. So it's a product of these two. I can of course change places of these two terms, and then I get the covariance of y and x. The next result tells us that the covariance goes inside linear functions. So if I have a covariance of the sum x plus y with z, I can calculate that as the covariance of x and z plus the covariance of y and z. This is not hard to show. the expected value of x plus y is equal to linear. So I can move the expected value inside. It's mu x plus mu y. That means that the covariance of x plus y and z is, according to the definition, expected value of x plus y minus the expected value of x plus y. That is mu x plus mu y. This one is to be multiplied by z minus mu z. If I just rearrange the terms in this parenthesis, we see that this is expected value x minus mu x plus y minus mu y. This is going to be multiplied by z minus mu z. I can then expand this parenthesis by multiplying this by this plus this times this. So that is equal to expected value x minus mu x, z minus mu z, plus y minus mu y, z minus mu z. I have a plus here, so I can move the expected value inside. Expected value x minus mu x, z minus mu z, plus expected value y minus mu y, z minus mu z. This is the covariance of x and z, and this is the covariance of y and z. So we have this result. It's easy to extend this result. If I have the covariance of a sum of 3 random variables instead on the left hand side, then I will get the sum of 3 covariances and so on. Number 8, the covariance of a constant times x with a constant times y. What you can do then is you can just pull out both of these constants outside, so it becomes a times b multiplied by the covariance of x and y. Again, not too hard to show by just going back to the definition. This is the expected value ax minus the expected value of ax is a mu x. Then we have by minus the expected value of by, which is b mu y. I can pull out the a from the first parenthesis, and I can pull out a b from the second parenthesis. These are now just constants inside the expectation, so I can pull them both out. So I get a times b times expected value x minus mu x, y minus mu y, and this is the covariance of x and y. The final covariance rule, which you may actually call a variance rule, is the following. The variance of the sum of 2 random variables is the variance of the first plus the variance of the second plus 2 times the covariance between the random variables. We see that if x and y are independent, then the third term disappears. We also see that if they're uncorrelated, so that the covariance is 0, then the third term will disappear as well. It is not difficult to prove this. We'll just use the fact that the variance of x plus y is the expected value of x plus y minus mu x minus mu y squared. We take x plus y, we subtract the expected value of that, and we square it. By just rearranging terms, this is expected value x minus mu x plus y minus mu y squared. If I do this square, I get the square of this plus the square of that plus 2 times the product. So this is expected value x minus mu x squared plus y minus mu y squared plus 2 times x minus mu x times y minus mu y. It's the expectation where I have sums, I can move it inside. Expected value x minus mu x squared plus expected value y minus mu y squared plus, I can take the 2 outside, constant, expected value x minus mu x, y minus mu y. This is the variance of x, this is the variance of y, and this is the covariance of x and y.